We're continuing the same problem as spacecraft in an elliptical orbit. Now part C, using conservation of energy, find the speed at perigee and the speed at apogee. Okay, now in the previous part we used the conservation of angular momentum to find the ratio of the speeds. And the conservation of angular momentum applies because we have no net external torque on the system. Now we have conservation of energy, that is the total mechanical energy, kinetic energy at the apogee plus the potential energy at the apogee must be equal to the kinetic energy at the perigee plus the potential energy at the perigee. We have energy conservation. Why do we have energy conservation? We don't have any dissipating forces. The system is isolated. There is no energy exchange, isolated in space. What is the kinetic energy at the apogee? It is 1 over 2 mass of the spacecraft, its speed squared. What is the potential energy? Minus g, gravitational constant, mass of the Earth, mass of the spacecraft divided by radial distance Ra at the apogee. This is equal to kinetic energy at the perigee 1 over 2 m Vp squared, and the potential energy minus g, mass of the Earth, mass of the spacecraft, radial distance between the two. So you can see that these m's will cancel, and we will be left with, if we multiply this equation by 2, so this is going to disappear, this is going to disappear, there will be a 2 here, this disappears, there will be a 2 here, multiplying it by 2, we obtain Vp square minus Va square equal to, so I have taken Va square to the right side, 2gme, 2g mass of the Earth. Now I have 1 over Rp minus 1 over Ra, the radial distance at the apogee. But we know from conservation of angular momentum that the speed at the perigee is related to the speed at the apogee. We have this result. Vp over Va is this ratio. So it is Re plus Ha divided by Re plus HP, this ratio, which is basically Va times the radial distance at the apogee divided by radial distance at the perigee. So for Vp, I can write this result. So let's substitute for Vp, Va times Ra over Rp. So I'm going to obtain Va square Ra square over Rp square minus 1. So taking it into Va square parentheses, this must be equal to 2g mass of the Earth. Now writing this in common denominator, Ra minus Rp, Rp product. All right. And if I write the left-hand side with the common denominator, Va squared, I have Ra squared minus Rp squared divided by Rp squared is equal to 2g mass of the Earth Ra minus Rp divided by Rp And I can see that one of the RPs will disappear. And for RA square minus RP square, I can use RA minus RP multiplied with RA plus RP. So with that, I will see this is VA square RA plus RP over RP, RA plus RP over RP, because RA minus RP part cancels with this one. And this is basically 2GME divided by RA. So isolating VA square here, this becomes VA square is equal to 2GME RP divided by RA times RA plus RP, and therefore we obtain our final answer. VA is equal to 2GME. For RP, I substitute radius of the Earth plus the distance from the Earth's surface, HP, divided by, for RA, I substitute RE plus HA, and here I have 2RE plus HA plus HP for RA plus RP. So this is our answer for the speed at the apogee. At the same time, we have the speed at the perigee. Vp square is VA square multiplied by RA square over RP square using the conservation of angular momentum. So we find that Vp square is 2GME RA divided by RP times RA plus RP. So basically multiplying this by RA square over RP square. So we will have RA remaining on top and RP remaining at the bottom. So if you multiply this by RA square over RP square, there will be RP remaining here and RA remaining here. That gives us this result. And therefore, we have our final answer for the speed at the perigee. Vp is equal to 2g mass of the Earth Re plus Ha divided by Re plus Hp 2Re plus Ha plus Hp. Now we can substitute the numbers to get the numerical results. Radius of the Earth is 6,370 kilometers. Mass of the Earth is 5.97 10 to 24 kilograms. Gravitational constant is 6.67 10 to minus 11 Newton meter square divided by kilogram square. HP is equal to 400 kilometers. HA is equal to 4,000 kilometers. So with that, we obtain for VA is equal to, we will substitute the numerical values, 2G, 2 times 6.67, 10 to minus 11. Mass of the Earth, 5.97, 10 to 24 kilograms. 2G mass of the Earth, Re plus HP. So we have 6.37 10 to 6 meters for RE. For HP we have 4 times 10 to 5 meters divided by RE plus HA. So we have 6.37 10 to 6 plus 4 times 10 to 6. And then we have 2RE, 2 times 6.37 10 to 6 plus 4 10 to 6 HA and 4 10 to 5 HP, and all this in square root. So this gives us our numerical answer to be 5.51 10 to 3 meters per second. That's the speed at the apogee. And as for the speed at the perigee, Vp, it is Va times Ra over Rp, which is Va times Re plus Ha, Re plus divided by Re plus Hb. So this gives me Va times 6.37 plus 4 10 to 6, 6.37 plus 0.4 10 to 6. So this gives me for Vp 8.43 times 10 to 3 meters per second. That's the speed at the perigee. Part D of the problem. It is necessary to have the spacecraft escape from the Earth completely. If the spacecraft's rockets are fired at perigee, by how much would the speed have to be increased to achieve this? What if the rockets were fired at apogee? Which point in the orbit is more efficient to use in order to escape the Earth? Okay, so to escape from the perigee, we have the total mechanical energy 1 over 2 m Vp prime squared for the escape speed minus g mass of the Earth, mass of the spacecraft divided by radial distance at the perigee. This must be equal to minus g mass of the Earth, mass of the spacecraft over R final with zero kinetic energy, and R final goes to infinity, so that is escaping, so this is going to be equal to 0. So we find that the escape speed at the perigee, Vp prime, is 2g mass of the Earth divided by radial distance at the perigee, square root of all this. And for that, we can substitute for the escape speed 2g mass of the Earth divided by Rp, which is radius of the Earth plus the altitude from the surface of the Earth, square root. And now the question is, how much is the change in the speed that we need in order to obtain this result, that's successful escape? Now our final speed that we would like to reach is the escape speed, which is 2g mass of the Earth divided by Re plus Hp square root, escape speed at the perigee, minus the actual speed at the perigee that we have calculated, which is 2g mass of the Earth Re plus Ha divided by Re plus Hp, 2Re plus Ha plus Hp, the whole thing in square root. So that is the change in the speed that we need in order to obtain successful escape. All right, and we can calculate the numerical value of the escape speed here. Vp prime is, if we substitute the numbers, 2 times 6.67 10 to minus 11, 5.97 10 to 24 kilograms divided by 6.37 10 to 6 meters plus HP 4 times 10 to 5. So this is 6, this is 5. Let's do this again. This is 10 to 6, this is 4 times 10 to 5, and all this in square root. This will give me a Vp prime escape speed of 1.085 times 10 to 4 meters per second, so that the delta Vp, if I subtract this from the escape speed, from the speed I've calculated in part C, I find delta Vp to be 2.42 times 10 to 3 meters per second. That's the increase in the speed I need in order to obtain this escape. So that's where I fire the rockets. And in order to escape from the apogee, I'm going to do the same calculation. Now I have 1 over 2 m VA prime squared, the escape speed, minus g mass of the Earth, mass of the spacecraft divided by RA equals to 0. This gives me an escape speed VA prime 2gme over RA square root, and VA prime is 2gme divided by RE plus HA in square root. That's the escape speed. So the amount of increase I need in the speed of the spacecraft with the help of the rockets is the escape speed that I have found, which is 2gme over RE plus HA square root minus the speed I calculated at the apogee, which is, without the rockets, 2gme RE plus HP divided by RE plus HA, 2RE plus HA plus HP. This is also in square root. And that's the symbolic answer for the increase in the speed I need. And if you plug in the numbers, you find that the escape speed from the apogee is now 8.763 times 10 to 3 meters per second. The original value was 5.51 10 to 3. So this implies a delta V at the apogee that is required is 3.25 times 10 to 3 meters per second. Okay, what is the conclusion? Since the necessary increase in speed is less at the perigee, it is 2.42 10 to 3 as opposed to 3.25 10 to 3, the perigee is more efficient to use for this purpose. So what one should do is to fire the rockets at the perigee in order to gain this additional speed and escape from the orbit. Okay, so in this part of the problem, we talked about energy conservation of the isolated system in order to calculate the speeds at the apogee and the perigee. The initial mechanical energy is kinetic energy 1/2 mva square minus g product of the masses divided by radial distance between them. That's the potential energy. This is equal to the kinetic energy at the perigee plus the potential energy at the perigee. And we can solve for VA and VP from this equation, which is what I did here, and plug in the numbers to obtain the values of the speeds at these points in the orbit. Now, in part D, we were asked to find, in order to achieve escape of the spacecraft from the Earth completely, where to fire the rockets. Because the amount of increase in the speed we would need to achieve the escape would be different at these 2 points. Which one is more advantageous? So we looked at escape from the perigee. The total mechanical energy will be equal to 0. So it's going to escape. So it's escaping to infinity. The potential energy goes to 0. Kinetic energy goes to 0. So we have the speed just to achieve the escape with no additional kinetic energy. This gives me square root 2g m over r for the perigee and for the apogee. And subtracting this from the value we have found in part C, we find that delta Vp is 2.42 10 to 3, delta Va is 3.25 10 to 3. So this is less, so less of an increase in the speed is required to achieve the escape at the perigee. Therefore, the firing of the rockets should be done at the perigee. It will be more efficient.